In this video, I'll be going over the Lorentz force from the spacetime algebra paper. Before I begin, I have some stuff written out. A useful background for this topic is the video I made, Special Relativity in 3D Geometric Algebra, Spacetime Rates, and Eigenspinors. Because in this video, I derive the Lorentz force from this equation, or I derive it to be simplified to this equation, but the approach that is used to derive the Lorentz force law in 3D geometric algebra is related to the spacetime algebra approach. And that makes sense because the 3D algebra or geometric algebra is just the algebra of physical space, which is isomorphic to the even subalgebra of the spacetime algebra. So when you break things in the STA into a relative frame, you're actually working with stuff in here. So if you want a background on this that's like pretty in-depth on the derivation of this, then you should go here. I'm not going to rederive it here just because the entire video pretty much was spent on the derivation here, so that would just be me redoing that. But you can still learn the Lorentz force law in the STA without this. It's just in case you want to see it. However, there's a little bit of background that's necessary. So what is the Lorentz force? So the Lorentz force has two aspects of it. So there is I'll do this. There is a time component, and then there is a spatial component. So the time component here is given by, so like the change in the time component of the momentum, of the 4 momentum, is equal to E over C, the electric field dotted with the vector, So you have the electric field and you have the vector v signifying the motion of the particle, how fast the particle is going, the velocity. Then you have the space-like component, so the spatial component, which is given to you by, no, actually, hang on, I forgot over here to put gamma, and there's a gamma out here, gamma E, and then E plus V cross B. And so this will give the actual, like, at a moment in time, this will give the force, the Lorentz force on a particle with a charge E, because it's known that the magnetic force, or the electric force of a particle is E, the charge times the electric field, and then this gamma just accounts for time or length contraction, or so relativistic effects. This would be the force, the electric force, but then the magnetic force would be equal to gamma E V cross B. So when you add these up, you get the total spatial force, and then here is the change in its momentum through time, which is just the same thing as saying it's change in energy, essentially. So this gives you the change in energy of a relativistic particle, charged particle, and this will give you its acceleration slash, or so its path of, or its equation of motion. But that can all be kind of simplified. That can all be simplified into one thing. So this is just a 4-vector. Traditionally, I could write traditionally a 4-vector. So relativistic 4-vector, where you'd have PT, PS, this is a vector, equals gamma E over C E dot V gamma E E plus V cross B. And then actually I'll write the 4-vector like this. These angle brackets are traditional ways to write a vector. So if you put an angle bracket and then a comma and you have components of the vector here. So this is a 4-vector. This represents the 3 spatial components. And this, so there'll be three scalar components in here. You'd end up with, this would basically give you px, the momentum in the x direction, momentum in the y direction, momentum in the z direction. But the reason I'm not writing out each individual component is because then I'd have to actually expand this into components, and components are messy. And I guarantee you expanding this into components will not help your intuition at all. The intuition comes from these products. So we need to go about deriving this from the spacetime algebra. So in geometric algebra, in GA, forces are generally given by commutator products. Motivated, or so let's rather say, let's consider the commutator of a spacetime rotation rate which this is just a bivector. So a spacetime rotation rate, commutator of a spacetime rotation rate, and momentum. So relativistic momentum P is equal to the mass times W, which W is the relativistic or velocity. So you have gamma C, gamma V. Oh, and I was going to write it up here, but I kind of forgot. a thing to note is that gamma, when it's written without subscript, is the same thing as the cosine of phi, where phi is equal to the inverse tangent of the velocity, the magnitude of the velocity vector, over c. So this is called rapidity, and gamma is the cosine of the rapidity. And you'll see this written more traditionally in literature as 1 over square root of 1 minus v squared over c squared. But these are the same thing. We're not going to get into this derivation right here, but these are the same thing. And that's what this gamma is right here. So you have the mass of the particle that's moving times gamma c and gamma v, where gamma c, this is of course how fast it's moving in time. This is of course how fast it's moving in a relative frame. So perhaps I should emphasize that this v is a vector. It's a relative. It's got this out here. So when you bring out the gamma naught, this is what this vector is. So this c is a scalar speed of light. This v is a vector, or a relative vector in the spacetime algebra. So it's actually a bivector with time-like components. Anyway, we're going to consider the. Let's move things. Let's move things a little bit this way, just so I can write this. So we can have a spacetime rotation rate. Going back to where we were. We are considering the commutator of a spacetime rotation rate bivector, which is omega, and a relativistic momentum p. So the change in time of p, dp dt, is given by 1 over 2 omega p minus p omega. This is just a common geometric algebra result, is that the change in time of some quantity is a bivector commutator product with the object that's changing in time. And so a force is just the change in momentum of time. So you have some bivector commutating with this, so it's a change in time of the momentum, so force. Well, this p is a vector in the STA, and this omega is a bivector. So this just defines the dot product, the inner product between omega and p. But let's just continue expanding this out and see what we get. So let's break everything in here into a relative frame. So for the sake of argument, we'll say that omega here in a relative frame is equal to, it's really hard to come up with a good symbol here. I'll just say omega 1 plus omega 2 I. We'll say that this is the relative split of omega. So we can split this up, omega 1 plus omega 2 I. And then we get m gamma c plus m gamma v, and then we get minus m gamma c plus m gamma v, then omega 2I minus omega 1. And here I'll explain these minus signs in a sec. Gamma naught. So to do the relative, or to split this into a relative frame, you pull out a gamma naught to the right, just as you traditionally do for a spacetime split. And here, when you pull it out to the right, there's no negative sign. So you're pulling out the gamma naught from the right here, so there's no negative sign, it's all positive. And you're pulling it out from right here, so there's no negative sign. But to pull out the gamma naught from here, it has to commute with this bivector. It commutes with omega 2, and it commutes with or here, hang on, does it? It anti-commutes with omega 2 and anti-commutes with I. So as a whole, gamma naught commutes with this. But it anti-commutes with this, so it gets a negative sign. So we can then distribute this minus sign into here. So we get 1 over 2. I am not copying this all by hand again. Uh-oh, what the balls? Okay. So distributing a minus sign makes this plus, makes this plus, and makes this minus. So this minus becomes this. And if you'll notice, this is just momentum p in a relative frame, and this is momentum p in a relative frame. This is just omega in a relative frame, and this is omega with some action done to it. And this is actually the exact same form as this, where this is the relative reverse. So the reverse in the algebra of physical space. So you can see that these forms here, this form is equivalent to this form. Except remember there's a gamma naught out right here, which doesn't show up in here, but within this, it's the same as that. Cool. So we can then expand things out even more. 1 over 2. We'll get this is basically, or this times this is going to be just this is just a constant, and this is a bivector, so you're just going to get bivector, and you have two factors of it, so you have 2 m gamma c omega 1. Then you're going to have omega 2 or omega 1 times this, and then this times omega 1, so you end up with omega 1 m gamma v, which you can then pull out this m gamma. Like this, gamma v plus v omega 1. And then you're going to have just this constant times omega 2I, but then you're going to have minus omega 2I times a constant. So this and this will cancel each other out. So you'll only have this times this times this, which gives you m gamma omega 2I v minus v omega 2I all of this with gamma naught out to the right. Now we can switch. What I'll do is I'll switch this around. So this will just be equivalent to having a minus sign. So if I put a minus sign in front of everything, then this becomes inverse, inverse, minus. So by introducing a minus sign and then introducing another minus sign, so this absorbs a minus sign. And when you absorb it, it switches it, so it looks like it's now V omega 2, then omega 2, V. But we can actually rearrange this because they commute. So actually what I will do is take this, that, I'll pull this out. And this is just the definition of the cross product. So we can now distribute this 1/2 into everything here. We get M gamma C omega 1 plus M gamma omega 1 dot V plus M gamma V cross omega 2. All of this, of course, gamma naught. Okay, let me turn that on. And we can then simplify one last time. M gamma C omega 1 plus omega 1 dot V plus V cross omega 2. But what is this exactly? If we look back up to this, we can see that we have some bivector dot with V, and looks like we have some form like that here. And then here we have some gamma times E, and then a cross product. But here we'll have a gamma times something, and then times a cross product. So it looks like this has all of the same math that's traditionally in the Lorentz force. And it turns out that this does give the Lorentz force. So we choose omega equal to E over mc, and then F, where F is just the electromagnetic field. So E plus BI. I'm going to do something here, though. The entirety of the STA paper works with the electromagnetic field like this. However, to get the units correct, because the electric field and the magnetic field do not have the same units. To get the units correct, I need to multiply by the speed of light here to get the units correct. So this is just all I'm doing. The math doesn't change. You could do all the math without the C here, but just if you're getting the units correct, I'm going to put the C there because that'll make it agree with everything up here. And you might wonder why we would choose this rate. Well, it would be from the physical intuition of this represents a rate of change that generates some force. Well, the rate of change between an electric field and some charge E would have to be, so you have the charge E interacting with the magnetic field, and then that force depends upon the mass. So you have kind of like a force per mass ratio, and that's what the rotation rate is telling you basically. And then when it acts on the momentum p has some some mass that will cancel out with this, and that'll then give you the rotation rate, or that'll give you the force from the rotation rate. So it's not like it was chosen without reason. It was chosen by the physical intuition of, we know a charge interacts with the electromagnetic field, and that depends upon the ratio of that and the mass. But then when you actually put this all together, we'll see that the mass cancels out. So if we choose this, then we can go directly into this form by making this observation. Then omega 1 is equal to E over mc, the electric field, and omega 2 is equal to E over mc b. So now we can put all of this in. So therefore, the Lorentz force, which is equal to E over mc F dot P, this is going to be m gamma. So I'm just doing direct substitution of these values into this equation. C E over mc, then omega, or sorry, E plus E over mc E dot V plus E over mc V, or yeah, no, V cross B. And if I fully expand this, or fully cancel out all the terms, the m cancels here, the c cancels here, the m cancels here and here. We end up with just gamma times E plus, or yeah, no, plus E over C. Oh, sorry, hang on 1 second. I forgot that there's an extra, I did fix the units here, so I put a C here, which means that this C cancels out, so this C goes away. So it's just E over M, the gyromagnetic ratio, or I'm pretty sure it's something like that. Magnetic ratio to, no, gyromagnetic, is it? I don't remember the exact word, but this is an important ratio in physics, so it makes sense that it shows up here. So you get E over C, E dot V, and then this M cancels out, so you get plus E V cross B. Well, what we can do is pull out an E to the front here. So this just becomes a 1. Move this over here. Gamma naught. And looking back, up at this form right here, see that there's a gamma E, E, gamma E, E, gamma E 1 over C E dot V, gamma E over C E dot V, and then gamma V cross B, gamma V cross B. And actually what should be a better form is if I instead put this back, copy, then move this out front, put this in here, and have this. And this looks exactly the same. So E dot V, E dot V, gamma E, E, V cross B, V cross B. So you have exactly the same formulas. So the rate of change given by the commutator product here, when you have the correct field, will give this, which is the Lorentz Force law. So you could have, we could have also done something else to derive it. So we could have considered charge momentum. We could have considered charge momentum. It's a good letter for charge momentum. I'll just do this. Charge momentum, electric charge times W, where this W here is the same W that we used up here. So gamma C plus gamma V and then gamma naught. So this basically tells you where the charges are moving in space-time. So it's called charge momentum because it tells you where they're moving. So you could have considered charge momentum and then used this to derive the Lorentz force law. So you could have said that the change in time of momentum is F dot EW. This would have given you the same result. I'm not going to derive it just because it would require me to plug stuff all in again, but you can see that this has no mass term, so there's no mass overall in the end result, and it has E, so the E would distribute just like this. And so you'd have the exact same result as before. If you want, you can go from this equation and just plug this in here and then work it out for yourself. That'd be a really good exercise. But again, I'm not going to do it because I've pretty much done exactly the same math you need for it twice. So what if there's magnetic charge? So what if the charge is complex? And this is the same thing as saying has magnetic charge. Again, there's this whole thing where it doesn't really exist, but it's important for the math. So consider Q, which is equal to E, where E is the charge that I'm going with, then E theta I. It's confusing. These are two different E's. This is the electric charge E that is used in physics, and this is Euler's number. It will always have an exponent, so just know that these aren't the same as a joke. These are not the same. Okay, this is equal to E cosine theta plus E sine theta I, which we'll just call call this the electric charge plus the magnetic charge, I. So this right here, this side of the equation implies this thing right here. Qm over Qe is equal to tangent of theta. This will be useful in the next video where we consider dual symmetry with source charges, but we'll return this again to the next video. It's not important here. Oh, I didn't want to group it. So what if we were to consider the magnetic force law there? So the force would be you have the change in time of momentum, and we're going to consider using this approach right here where we're actually going to have the charge momentum and it's going to be complex. So it's going to be F, it's going to be 1 over 2 F Q minus Q F and this is going to be equal to 1 over 2 so oops, no, we don't want to consider Q, sorry. We want to consider this quantity right here. So we want to consider Q. This is complex charge momentum. So we have the momentum and then Q here. So WQ, WQ, which is going to I'm going to skip to the end result here because the math here, expanding this out is just the same as expanding all this stuff out. So I'm going to just skip to the end result. You get Q, the electric charge, times the dot product of the velocity, W, plus the magnetic charge of F wedge W. Which is this? I can't. I'm looking at my notes. I will talk about this one. Okay, I think I made a mistake in my notes, so I'm going to go back over this and I'll cover this briefly in the beginning of the next video.